Hey guys, thank you for joining. I know you guys have a ton of options with respect to breakout sessions, so I appreciate you taking a little bit of time to talk about simulation and specifically about the Explicit Solver that's now available on the 3D Experience platform. I realize, we would all rather be there in person, interacting with one another, but it's been a weird year, and I appreciate the opportunity to get to present this to you guys. Hope everybody is safe. And let's go ahead and get started. All right, guys, so let's start by discussing what the agenda is going to look like. We're going to start by discussing exactly what explicit is, situations where explicit can be beneficial, the difference between implicit and explicit, and why it's a very important solution technique, especially for short duration, kind of high energy types of events. Then we'll talk a little bit about the 3D Experience platform and the SIMULIA tools that are available on the 3D Experience platform. Really exciting time to be a SOLIDWORKS user because you're going to have access to a lot of really improved solution techniques from SIMULIA. We'll walk through a few examples. The examples are going to highlight some of the capabilities that Explicit has, some advanced capabilities like damage modeling and smooth particle hydrodynamics. We'll show some videos of other examples that you'd be able to solve. Then we'll have a summary, and then we will open the floor to questions and answers. Okay, so what exactly is explicit? So let me give you a little bit of background. Back in the early 80s, Abacus developed their implicit solver. That's the standard finite element analysis solver. It's extremely good for nonlinear problems, ill-conditioned contact, complex material problems. It's arguably the best-in-class finite element analysis solver on the market. Great for, again, general nonlinearities. Obviously, it can do linear simulations, and for multiphysics like, heat transfer, acoustics, etc. In the late 90s, Abacus developed a second, completely different and independent solver with the explicit solver. It's really meant for short duration events. And it's really was developed for situations where the implicit solver starts to break down. So again, think of things like drop testing, crash testing, crushing, metal forming, those types of highly nonlinear, high energy types of events. And that's really the difference between the two solvers. Now, so again, the implicit solver is your standard finite element analysis solver. The explicit solver, completely independent and really meant for highly dynamic, short duration type of event. So this is a nice mathematical way to look at this. Think of it that you're driving down the road. In an explicit solution scheme or an explicit driving scheme, you can't see anything in front of you. You can only drive based on looking in your rearview mirror. In an implicit scheme, the blackout in front of you is gone, so you can see what's in front of you, but it's really foggy. So as you get closer to the end result is going to get clearer, and you're going to converge on the final state. So what that means, when you're driving and you can only look in the rearview mirror, you have to take extremely small steps. So the explicit time scheme has the explicit solver has some really stringent requirements on the size of the step you can take. With the implicit solver, you can take larger steps, but when you have really short duration events and that have large changes from the previous step, the implicit solver starts to break down. Explicit also takes advantage of a computationally efficient technique of using the lump mass matrix. So that's extremely economical, and that's not unique. That's kind of common across explicit solvers. You also have to use a lot of time increments, but they're very economical. So it's different from implicit, where you have to invert a system matrix and iterate until you get convergence. So what are some of the benefits of using explicit? Well, first, this solver is really designed to solve highly discontinuous problems, so high-speed dynamics problems. It's got a very robust general contact algorithm. It doesn't require as much disk space as implicit. It removes some of the issues associated with non-convergence of the Newton-Raphson method. And it's really well suited for quasi-static problems. So, large deformation, static instability, ill-defined contact. for mildly nonlinear problems, and even some more highly nonlinear problems, you can probably still use Abacus implicit, but there's definitely a cutoff where it makes sense to move to an explicit solution technique. Let's take a second now and discuss a little bit about what's going on at Dassault Systems. So for those of you that don't know, SIMULIA is a brand inside of Dassault Systems. And SIMULIA is basically the brand that's responsible for developing all of the simulation tools that Dassault has. So even the structural or the desktop solver on the SolidWorks side is developed by SIMULIA. Again, the flagship product probably of SIMULIA, I would argue, is Abacus, right? The structural solver. This graph represents the acquisitions that have been made in the last 20 years by Dassault in the simulation space. And what you see is, products for electromagnetics, computational fluid dynamics, plastic injection molding, durability. So Dassault has a long-term consistent commitment to simulation, and that commitment is being met by the SIMULIA brand. And when we talk about 3D experience and the 3D experience work set of solutions, what those are basically, so a handful of years ago, anybody who uses SolidWorks Simulation Premium knows that it hits its limits sometimes, right? So the decision was made, instead of really enhancing that solver, why not leverage the Abacus solver, which is best in class? So, this chart kind of represents the way we think of the simulation space as well as the simulation tools that are available inside of Dassault. So on the designer side, you have, and I would argue that Simulation Premium probably goes a little bit higher than designer, right? But you basically have tools that are really, really geared towards designers and engineers. Those tools are tightly integrated with SolidWorks. Now, way on the right side of that graph, you've got Abacus CAE, which is for analysts. It can do basically any structural analysis you would want to do, Abacus would be able to do. What the SIMULIA tools on the 3D Experience platform are a step up from Simulation Premium and a step to the left from what Abacus CAE can do. So it doesn't do everything that Abacus CAE can do. It's a new interface on the 3D Experience platform, much more user-friendly and intuitive. Allows you to leverage your SolidWorks geometry. So it's really tightly integrated with SolidWorks, and that is where the future of Dassault is. So, I would think that in the coming months, the coming years, you're going to see a lot more tools from SIMULIA on the 3D Experience platform that are geared for SolidWorks users inside of that 3D Experience Works portfolio. Okay, guys, so if we think about what are really the overarching benefits for utilizing the SIMULIA tools on the 3D Experience platform, these are kind of the 3 bullet points that I hope resonate, right? First, it's powerful. It's using the Abacus solver. So problems, that hit its limits using the desktop solution are going to be able to be solved using Abacus. It's integrated with your SolidWorks geometry. So, if you want to make design changes, it's going to be linked to your SolidWorks model. You're not going to have to reset things up. The parametric optimization is out and released, and it's only going to get better, so the ability to do design optimization, and it's cloud-based. So if you want to leverage cloud computing and utilize the Abacus Cloud to solve your problems much, much more quickly, that is also going to be something that's available. So I don't want to talk a lot about kind of the way roles and apps are distributed on the 3D Experience platform. I don't think that's as important for you. I just want to point out, when you're thinking SIMULIA and the 3D Experience platform tools, there are 2 ways to do dynamic analysis. There's the implicit solver that's available in a role called structural performance engineer, and there's the explicit solver that's available in structural mechanics engineer. And if you purchase structural mechanics engineer, you would get the implicit solver too. So you get all of the capabilities inside of structural performance engineer, in addition to the explicit solver and some other apps that are included with structural mechanics engineer also. All right, so that being said, with a little bit of review, let's now talk, let's move to the examples, right? So the first example that we're going to highlight is a can crush. So the intent here is to model our can, and then we're going to apply a velocity that drives the can down and basically crushes it onto itself. So think of it like, standing on top of an aluminum Coke can or something. This would be something that you really wouldn't be able to solve in an implicit, and there are a lot of benefits of using the SIMULIA tools, particularly in this case the way Abacus handles general contact. So that'll be something that we want to highlight and discuss. Okay, so if we look at this model, the first thing that you'll notice is we're using a coupling at the top. So the coupling is going to drive the displacement. We're modeling the bottle as a shell. The top and bottom plates are being modeled as solids. And one of the things that we can take advantage of is a surface quad mesh. Another really nice feature is that we can let the thickness of our shell body be defined by the actual geometry. So you can see it's got a variable thickness. The can itself has a variable thickness based on the thickness of the actual geometry. So if we look a little bit more at the setup, the first thing you're going to notice here is that we're using a brick mesh. So one of a nice feature that wasn't available inside of the SOLIDWORKS desktop tools is the ability to generate a hex, or a brick mesh. We're going to apply initial velocity to the top plate, and we're going to retain that velocity throughout the displacement. We're going to, just clamp the bottom so that it's fixed. A great feature is I'm just using general contact here. So the assumption is that with general contact is that any faces that come into contact, whether they're initially touching or not, are considered like a no penetration contact. So let's take a look at our results real quickly. All right, so we're kind of looking at the end result here. Let's go ahead and animate this thing. But you can see all the results for each of the individual steps. We can control how much is saved throughout the run. And if we click on the animation button, what we're going to see here is that it's going to walk through and create an animation. Now I'm looking at von Mises stress here, but you can see that can is collapsing on itself, just like what would happen, if you really were standing on a soda can, right? But think about all the contact that's going on there and the benefit of not having to manually specify contact pairs, whether it's self-contact or just ill-conditioned contact problems. Look at the ease with which the Explicit Solver has in solving this type of problem. So, really, really simple for the Explicit Solver to reach a converged solution. So once it goes through, after it's created that kind of initial walkthrough, much faster playback times. Can also look at things like contact pressure. Obviously, you've got a whole host of post-processing capabilities and tools that are available. I'm going to go ahead and you can see that the contact pressure being generated as those faces are collapsing on each other. It's staying in the blue in this case, so we could reconfigure our contour plot so that we had some red areas. But, again, very, very easy to generate this type of result. And this is really a type of problem that we would not have been able to solve using the SOLIDWORKS desktop tool. And it just runs so quickly and easily using the Explicit Solver provided by Abacus with using Structural Mechanics Engineer. So the first example, we can also do things like generate XY plots if that's something that you're interested in. So if you wanted to take a look at like the force versus displacement curves, we could do that also. So a whole host of post-processing capabilities and a relatively complicated example, but one that is very easily solved using the Explicit Solver here. All right, so example number 2. Another crushing example, but we worked with a bottling company recently, and they had a few examples that were pretty common for them. And one of the examples was that they have a bottle and it's filled with liquid, and they want to see what happens when they crush that bottle. So one of the advanced or more high-level capabilities that's available with these SIMULIA tools is the ability to model what are called Sph elements, so smooth particle hydrodynamics. It's a way to mimic a fluid in this case. So it could also mimic just a structure that's able to kind of break apart. It's often used for like, birds crashing into engines, or it's used sometimes to model like sand traps for golf. So it's an interesting example, and let's go ahead and take a look at exactly how we would solve that utilizing structural mechanics engineering the Explicit Solver. So let's take a look at the second example. It's a similar kind of use case in that we're crushing in this time a plastic bottle. And we'll start here looking at some of the results. So in this case, what we've done is we actually have SPH models to model the fluid inside. So let me just change the display here to make it a little bit more transparent so you guys can see. We've modeled that fluid volume with SPH, smooth particle hydrodynamic elements. And as this bottle is crushed, we can see the fluid start to evacuate from the bottle. So again, a class of problem that we really could not do inside of the desktop simulation tool in the past. Just a really advanced type of analysis. If we take a look at the mesh, you can see I'm taking advantage of hex meshing the surface, the shell for the bottle. I've also created a shell mesh just on the top and bottom blocks that are being pushed down and clamped. You can see some of the different types of meshes that are available inside the platform, much more control and different element types as well as formulations are available. Now, with respect to the SPH, I've modeled that as a volume, and the tap mesh was put on that particular bottom. So similar kind of setup using a coupling to push down the top. And again, utilizing the global no penetration kind of general contact condition that's available from the platform. In this case, the only difference is I've specified a friction coefficient. So you can see I've manually created what I'm calling friction coefficient, which basically does just that. It specifies what the friction is going to be when the bodies come in contact. So you can see I've specified the tangential behavior to be about 0.1 for those contact pairs. Now, obviously, if you wanted to bond things together using a similar technique to the desktop SolidWorks tools, you could do that. If we take a look at just some of the material formulations, like for instance, what are we using to model the fluid? You can see I created a material. It's called bottle drop. And if we take a look at that material, you can see I just really need to specify the density and the viscosity. So real common material properties that are available for fluids. And that really that sets the behavior for the fluid inside of the bottle. So SPH can be used in a lot of different types of situations. So in some of the videos I'll show in a bit, we'll see some other situations where we can use SPH. Now, if I take a look at the materials, I wanted to point out definitely some more advanced material models are available. So you can see all of the different hyperelastic. Hyperelastic is available. There's different hyperelastic formulations that are available. Obviously, can account for metal plasticity. Things like nitinol were added recently, and then the hydrodynamic settings for that fluid domain. And then if we just really quickly take a look at the scenario, you can see clamping the bottom and simulating the top. I mentioned earlier utilizing the cloud. If you wanted to do that, you can just say that instead of solving locally, you're going to solve it on the cloud. And you would need to acquire some credits that allow you to solve on the cloud. But the speed up is very, very linear when you're solving on the cloud. So if it takes 1 hour solving on 4 cores locally, if you run it on 8 cores, it's going to take half that time. So really great utilization of multiple cores. It's the solver is really written for those types of simulations and large models. All right, so our final example is going to be a blade crash. So in this case, we're going to also take a look at damage modeling. So that's something, again, another advanced capability that's available with the SIMULIA tools. we're going to model that pole as a rigid body, and we're going to see what happens when we spin the blade or the fan up, and the blades are in a position where they're actually going to impact that rigid body. So another real interesting kind of example, and we're going to be able to take a look at exactly some damage modeling also. Okay, so let's take a look at this model now. So the main difference here is that we're going to be utilizing, we're going to include damage modeling for the blade. So again, using a coupling to rotate the fan body. And I'm actually modeling the bar as a rigid bar. So it's going to be modeled as a rigid body just to reduce computational time, using a sweep 3D mesh for the bar and then a TEP mesh for the fan and the fan blades. If we take a look at the material properties for the fan, what I've added is damage behavior. So what happens after the material hits the ultimate stress and starts going down? And you can see I'm just having, it's basically a straight cutoff from the ultimate down to the hydrostatic cutoff pressure. And then I'm telling it to remove the elements that have failed. So once it exceeds a specific stress value, you're going to start seeing elements go away. So, you could potentially, with a fine enough mesh, model something like crack initiation and propagation, or if you did have a notch to model a crack, you could certainly model the propagation of that crack. Explicit time's about 0.02 seconds. Again, these are short duration kind of events. Same using that no penetration contact and a friction coefficient of 0.01, and clamping the rigid body, and then just applying an initial rotational velocity as well as maintaining that rotational velocity throughout the run in this case. So, the setup for these models are not very different than when you typically would run, a standard FEA problem. It's just the type of results that we can get are so much more powerful, especially, for this class of problem, if this is the space that you play in, right? So let's go ahead and take a look at the results. I'm going to animate this, and you guys are going to see some really cool behavior here. So when the fan blade hits, you can see those elements that exceed that stress value are disappearing. Now, I don't have a fine enough mesh. I should have made the mesh much finer in that region where the blades connect to the rotor in order to really capture those elements being eliminated, right? So damage modeling, very cool, but you're going to need to ensure that you have a fine enough mesh to really capture what's going on at those really high stress areas, right? So when this type of behavior is present, you can see the fans actually start banging against one another. Just a really complicated problem here that there's just no way that you would be able to capture this using the desktop simulation, right? Forget about damage modeling, but just, the behavior of the fan hitting the blades. The Explicit Solver is so powerful inside of the SIMULIA tools. Okay, so let's take a look at some of the other types of examples that you can solve using the tools available, the Explicit Solver. So let's start at the top left, and we'll move from there. In the top left, you see an example of Sph elements being used again to mimic kind of a bird crashing into an airplane, a wing, or and you would hope that, either the displacement is turned up quite a bit there, or the material for the wing is very compliant. The second example is thermoforming. So another really cool kind of analysis that you'll be able to solve using the platform Explicit tools. The third one there on the top is a door impact. Again, a lot of components on the inside of that door, and you don't have to manually specify all those no penetration contacts, right? So the parts that are bonded together can be bonded, and then everything else can be handled via the general contact. Bottom left, an impact problem. I believe this is for an artificial foot or type of problem, and you can see kind of a drop test what happens if that hits the foot. The middle one on the bottom there, drop testing with Sph Elements. This was, again, kind of similar setup to what we did with the bottle crush, but instead of doing a crush, we're doing a drop test, and the Sph Elements are being accounted for. And then that one on the bottom right, another really cool example of wire crimping, right? How would you solve that using the desktop tools where you have to specify the contact pairs, right? Who knows what faces are going to be coming into contact with each other beforehand? So really powerful types of examples that you can solve using these tools. All right, so let's just briefly review. So first, the SIMULIA tools on the 3D Experience platform are very, very powerful, and they give SOLIDWORKS users the ability to really run some analyses that they wouldn't have been able to do in the past. They're also, the interface is much more user-friendly than the traditional Abacus CAE environment, right? So it's really got some of that SOLIDWORKS flair that you guys are used to. Obviously, Explicit provides a solution for those types of complex events. You know, it's got enhanced materials, contact modeling, material calibration, meshing, and just a lot of other advanced features. You can leverage cloud computing if that's something that's interesting to you, if you want to reduce kind of your IT overhead. And, you know, stay tuned because, like I said, this is a really exciting time to be at Dassault and in the simulation space because there's going to be a lot more coming in the future.